This is Module 5, Signaling Line Circuit. We're going to start today's presentation with an overview of the signaling line circuit. We're going to touch briefly on the styles of wiring and then cover the device capacity for each panel. We are then going to discuss the addressable detectors, the detector bases, and finish with the addressable modules. Starting with the signaling line circuit, or SLC, on the PFC-6000 series panel. This circuit is capable of being wired either Class A or Class B. Class B is the most common. The diagram in the upper left-hand corner is an example of Class B wiring. All the devices we are talking about today and the systems we are talking about today are addressable systems, which means that all of these devices get a unique address. So on this slide, I've written some numbers under the devices to represent the address. For example, the pull station is address 1, the smoke detector is address 2, and the module next to that is address 3. What happens is the panel will pull the devices, asking them what their current status is, and the devices respond back. Because of this two-way communication, there is no need for an end-in-line resistor at the end of this circuit. In this diagram, you'll see that the SLC circuit leaves the panel, and there's a T-tap creating two branches of the SLC leaving the panel. The important thing to note here is that T-taps are accepted on SLC circuits that are wired Class B. We'll next take a look at the Class A style of wiring, which is shown in the lower right-hand corner of the slide. What happens here is that the SLC will leave the panel, and it needs to be a continuous loop connecting all the devices, and then will actually terminate back at the same place it started. This type of wiring provides a greater survivability. If you have a break in the wire in the middle here, indicated by the green circle, all of the devices will still communicate back to the panel. The top row of devices communicate in this direction, and the bottom row of devices communicate in this direction. The break will cause a trouble at the fire alarm panel, but all the devices are still communicating. Your job specification, or an AHJ, will outline the style of wiring that is required for your project. When it comes to the type of wire that the panels will accept, they are very flexible. They will accept solid or stranded, twisted pair or straight lay, shielded or non-shielded, and the terminals on the panel will accept 12 gauge to 18 gauge wire. To determine the length of your circuit when wiring Class B, you need to add the distance of your branches. In this example, we have two branches, branch A and branch B. The total distance of your SLC would be the combination of the length of branch A plus the length of branch B. The chart at the bottom of the screen will help you to determine the gauge of wire that will work on your project. Another thing to consider is the resistance of your circuit. The maximum wiring resistance for the SLC must be less than 50 ohms. To make sure you are within these parameters, you can measure the resistance of your circuit. To do so, you will need to create a short at the end of one of the branches, removing power from the SLC by disconnecting it from the panel or the SLC expansion card. Then measure the resistance of the circuit at the panel or the beginning of the circuit. Just remember, it needs to be less than 50 ohms. Repeat this procedure for the remaining branches. The total DC resistance for the control panel to each branch cannot exceed 50 ohms. To determine the length of a Class A circuit, you need to measure the distance of the wire from where the circuit started through all the devices and then back to wherever the circuit is terminated. The same chart works for Class A wiring to determine the gauge of wire that will work on your project. To measure the resistance for your Class A circuit, you remove the power from your SLC and create a short on the returning pair of wires. I'm showing it here at the pull station, but it would be just after the pull station. Then measure the resistance at the beginning of the circuit. The total resistance needs to be less than 50 ohms. The device capacity that can be connected to each panel is different depending on which panel you are working with. The PFC-6030 is aptly named 6030 to indicate the point count. You can connect a maximum of 30 addressable devices, any combination of detectors and modules, to the SLC. Looking at the picture, we have two detectors and two modules. The MIDI module is monitoring a fire alarm pull station. There are 4 addresses being used out of the 30 available in this picture. The PFC-6075 allows you to connect a maximum of 75 addressable devices. So for this slide, we're using 4 addresses, the 2 smokes and the 2 modules, of the 75 available addresses. The PFC-6200 is very similar to the 6030 and 6075. It is a larger panel. You can connect 127 addressable devices to the main board of the PFC-6200. In addition, you can install an SLC 127 either in the fire alarm cabinet, a PSN 1000E cabinet, or an accessory cabinet. The SLC 127 provides an additional 127 addressable points. This gives the PFC-6200 a grand total of 254 addressable points, any combination of detectors and modules. The PFC-6800 is larger yet. Again, you can connect 127 addressable devices to the main board of the PFC-6800. In addition, you can install up to 7 SLCE expander cards. These cards can be mounted either in the PFC-6800 cabinet, a maximum of 6, the PSN 1000E cabinet, again a maximum of 6 per PSN 1000E, or in an accessory cabinet. Each SLCE 127 provides an additional 127 addressable points. If you were to install all 7 SLCE 127 cards, the system would have a maximum of 1,016 points. Again, any combination of detectors and modules. For detailed information on wiring and programming the SLCE 127, please refer to the recorded module on P-Link devices. Now talking about the SLC devices, starting with the addressable detectors. Potter has 4 addressable detector heads: the PSA, or photoelectric smoke detector, the PSHA, or photoelectric smoke heat combo detector, the FHA, or fixed heat detector, and the RHA, or rate of rise heat detector. We will cover a few details and features of each of these devices, starting with the most common, the PSA, or photoelectric smoke detector. The PSA has an adjustable sensitivity range that can be set by zone through the programming software. Its range is 1.1% per foot to 3.5% per foot. This is the percent per foot of smoke in the room. The default is 3.5% per foot. The PSA and the control panel work together to keep the sensitivity consistent. Over time, the sensor gets dirty. The sensor compensates for the dirt in the unit until it is out of range. At that point, the panel will indicate a dirty sensor. The sensor will then have to be cleaned or replaced. The PSA can be easily cleaned with a simple vacuum, compressed air, or a small paintbrush. We will see a short video demonstrating this after we discuss the PSHA. When the PSA is being pulled by the fire alarm control panel, the sensitivity can be viewed or printed from the control panel. To view the sensitivity from the fire alarm control panel, press the Enter key to access the main menu. From the main menu, select Option 5, System Tools. In System Tools, select Option 1, SLC Tools, and in SLC Tools, select Option 1, SLC Pinpoint. And here, enter the address of the device that you'd like to see the sensitivity of. So I'm going to enter address 5, and enter. And I can see that this is address 5. This is a photo detector. The day sensitivity is active since it's daytime. The current sensitivity is 0. Peak is 0 as well. The alarm thresholds are shown at day and night. It's currently not dirty. The drift is 0. And the maximum drift allowed is 1.8%. When multiple detectors are installed, you can use the up and down arrows to view the sensitivity of the other detectors. By printing the sensitivity, you can generate a sensitivity report of all the detectors connected to the system. These reports are useful during annual inspections and for finding detectors that are close to causing a dirty sensor trouble at the control panel. An example of this report is shown. Looking at this report, the information that is highlighted is customizable through the programming software. You'll notice I have 4 detectors. They each have a custom message, and their current condition is shown. The peak value is the highest condition that the detector has seen since its last power-up. It gives you the alarm threshold of the smoke detectors and heat detectors. It shows you the current drift of your smoke detectors, as well as the drift limit. When a detector reaches the drift limit, it will cause a dirty sensor trouble at the fire alarm control panel. The drift alert column indicates if this is in an alert status. When the detector is in a drift alert status, it will generate an email to those that receive email alerts. The last column indicates whether it complies with NFPA 72. For information on programming the sensitivity, as well as receiving the drift alert emails, please refer to the recorded modules on the programming software. The PSA also has a very low profile. When mounted on a standard base, it is less than 2 inches in height. It also has 2 indicator LEDs for 360-degree viewing. Typically, the LEDs flash when the fire panel pulls the device, and they latch on when the device is in alarm. These characteristics can be altered at the panel. The PSA also includes an insect screen to prevent foreign objects from reaching the chamber. The next detector is the PSHA, or the Photoelectric Smoke and Heat Detector Combo Device. This device has all the same features as the PSA, as well as a fixed temperature restorable heat sensor set at 135 degrees Fahrenheit. You can see in the picture the heat sensor on the left side of the device. The Photo Heat Combo device is typically used to provide a greater range of detection capabilities. Usually these devices will be called out in a job specification or by the end user. The PSHA also has a very low profile. When mounted on a standard base, it is about 2 inches in height. Unlike the PSA, the PSHA has one LED that is not flush to the device housing to provide the same 360-degree viewing. The LED characteristics are the same as the PSA. Both the PSA and the PSHA are UL listed with a recommended maximum spacing of 30 feet. For more information on detector spacing, placement, and special applications, please refer to NFPA 72. As previously mentioned, this short video will demonstrate how to clean the PSA and the PSHA. When you turn the detector over, you'll find 2 screws. These 2 screws need to be removed to allow you to disassemble the detector. Once the screws are removed, you can remove the top cover of the detector. Once the cover is removed, you will see the photo chamber. The bug screen will need to be removed to access the chamber to clean it. The bug screen is clipped on, so you'll need to wiggle it just a little bit in order to remove it. Once the bug screen is removed, the chamber is revealed. With compressed air or a small vacuum, you can clean out the chamber. You may also need to clean the bug screen itself. Once the device is clean, replace the bug screen, making sure that it is clipped, and then replace the cover of the detector, replacing both screws that you removed in the beginning. You can now return the detector to the base and rerun the sensitivity report. The detector will now show a clean sensitivity. Now continuing on with the detectors, we move to the FHA, or fixed heat detector. This detector is strictly a heat detector. This is the most common type of heat detector. The temperature sensor on the FHA can be set between 135 degrees and 185 degrees. When the sensor detects the temperature at which it is programmed, the device will activate. The LEDs on this device are similar to the PSA, with the 2 indicator LEDs for 360-degree viewing. The spacing of this device is dependent on the alarm set point. As the temperature setting increases, the spacing decreases. With an alarm set point between 135 degrees and 170 degrees, the maximum spacing is 50 feet. Between 171 degrees and 185 degrees, the maximum spacing is 15 feet. The RHA, or rate of rise heat detector, looks identical to the FHA. The detector operates on a rate of rise element and a fixed temperature sensor. The rate of rise portion looks for a sudden spike in temperature regardless of the starting temperature, usually 12 to 15 degrees per minute. A sudden spike may not necessarily reach the fixed temperature alarm set point. Therefore, this device will alarm at lower temperatures when a sudden spike is seen by the rate of rise sensor. In the event of a slow, smoldering fire, the fixed temperature sensor will alarm at its programmed temperature. The fixed temperature sensor in the RHA has an alarm set point between 135 degrees and 170 degrees. These 2 features encompassed in one device provide a greater level of protection for areas covered by a heat detector. The spacing on this device is similar to the FHA. At a fixed temperature alarm set point between 135 degrees and 170 degrees, the maximum spacing is 50 feet. Each one of the detectors we covered occupies one address on the SLC. The address should be assigned to the detector head before it is connected to the SLC circuit. For information on addressing the devices, please refer to Module 6, SLC Device Addressing. Moving to the bases that these detectors can be connected to, Potter has 4 bases for use with the detector heads that connect to the PFC-6000, the PFC-6075, the PFC-6200, and the PFC-6800. The AB6 or 6-inch sensor base, the ASB or addressable sounder base, the ARB or the addressable relay base, and the AIB or the isolator base. All bases will mount to a single gang, double gang, octagon, or 4-square back box. All of these bases also come with a locking feature. This prevents removal of the detector head unless an additional tool is used, such as a flathead screwdriver. Some projects will require locking bases, such as jails, schools, and hospitals. If the locking feature is not required, it can be removed by simply breaking the plastic tab or twisting it towards the center of the base. When ordering detector heads, the base is not included, so make sure to include the appropriate number and type of detector base for your project. We will cover a few details and features of each of these bases, starting with the most common, the AB6 or 6-inch analog base. The AB6 is the standard base used for mounting the detector head to an electrical back box. The terminals are marked S positive or S minus for easy installation and quick connection of the SLC wires. Moving to the ASB or the addressable sounder base, this base has an independent sounder that can be programmed as a single station, zone, or all-call sounder. This type of device is commonly used in residential or hotel applications. Single station refers to the sounder activating when the detector head attached to that base alarms. For example, in a single-room apartment, when the smoke detector activates, the sounder activates. Zone refers to the sounder activating when programmed, independent of the state of the detector connected to it. For example, in a 2-bedroom apartment, you would want both sounder bases in the bedrooms to sound if either of the detector heads was in alarm. An example of all-call would be a detector in a public space going into alarm, such as the detector in the hallway. We would want all the sounders in the units as well as the public spaces to sound. These types of scenarios are easily programmed in the panel's programming software. The sounder base produces a minimum of 75 decibels at 10 feet, which complies with UL 464. The sounder does need 24-volt DC power in order to operate. The ASB passes through the sound pattern sent to it from that particular power source. For example, if you have a PSN-64 Potter power supply, you can make one of the outputs send an ANSI temporal pattern to the sounder when it activates. 2 wires would run from the terminals of the NAC output on the Potter power supply to the ASB sounder base 24-volt power connection. In addition, the base also gets 2 wires from the SLC connection. A total of 4 wires will be connected to this device for it to work as intended. In the drawing, the red and blue connector cable is provided with the ASB. The ASB does occupy one address on the SLC. The address is independent of the address assigned to the detector head that will be installed on the base. The address should be assigned prior to installing the base on the SLC circuit. The ARB, or addressable relay base, has a built-in relay module. It has 2 Form C relays that can be programmed independent of the detector. The first relay is rated 8 amps at 30 volts DC and 120 volts AC. The second relay is rated 2 amps at 30 volts DC and 120 volts AC. The device is designed such that once activated, both relays change position. There is a dedicated LED on the base to indicate activation of the relay module. The relay will reset when the panel resets. The ARB does occupy one address on the SLC, and again this address is independent of the address assigned to the detector head that is installed in this base. The address should be assigned prior to installing the base on the SLC. The ARB is a 4-wire device similar to the ASB. The device requires 24 volts DC to operate the relays. Therefore, 2 wires from an appropriate power supply and 2 wires from the SLC will be connected to this device. Again, the blue and red connecting wires, as shown on the drawing, are provided with the device. The last base we're going to cover is the AIB, or isolator base. Before we talk about the base itself, I want to first discuss why an isolator would be used. To understand why an isolator would be used, we first need to understand what happens when a short occurs on the SLC. When a short occurs, say here, where the arrow indicates, it prevents communication on that circuit, effectively rendering the entire loop disabled. The panel reports all the devices missing. When an isolator is installed on the circuit, say here, as indicated, it will isolate the section of the circuit where a short occurs, allowing the remainder of the loop to continue to function as normal. This helps keep the integrity of the system as well as makes the area of issue much smaller when trying to find the short. When the AIB is active, an amber LED on the base will be steady on for easy identification. The AIB does not occupy an address on the SLC. However, due to the power consumption when a short occurs on the system and the AIB is active, there are limitations to the number of AIBs that can be installed on an SLC. When wiring an isolator base, there are 4 terminals for the incoming SLC and the outgoing SLC. As with the other special detector bases, the blue and red cable is included with this base. That covers all the detector bases that the different sensors can be connected to. Remember that the detectors do not come with a base, so be sure to include them on your parts list. Moving to the addressable modules. There are 8 addressable modules that can connect to the PFC-6030, the PFC-6075, the PFC-6200, and the PFC-6800. They are the APS-SA or DA, which is the addressable pull station single action or dual action, the MCM, which is the mini contact module, the SCM-4 or the single contact module, the DCM-4 or dual contact module, the TRM-4 or twin relay module, the MOM-4 or monitored output module, the CIZM-4, the conventional input zone module, or the SCI, short circuit isolator module. The modules that you see highlighted here come with a cover plate. All of them, except for the MCM and the APS device, mount in a double gang or 4-square electrical back box. The MCM can mount behind a device in a single gang back box. The APS mounts on a single gang back box. If a module is provided with a cover plate, that cover plate allows the status LED to be seen, which makes it easy to identify the device that is in an active state or not responding. The LEDs on these devices flash when pulled by the fire alarm control panel, that is the normal condition, and latch on when it is in an active state. If the LED is not flashing or latched, the device is not responding due to an open circuit. We're going to start with the APS or addressable pull station. The APS series addressable pull station has terminals that allow the signaling line circuit to be wired directly to the device and then exit to the next device in the loop. This device does take one address. It can be ordered as either a single action or dual action device. To reset the pull station, use the Potter WS93 key, which is the same key as used in the fire alarm control panel. This device mounts in a single gang back box. When wiring the SLC goes in and out on the same pair of terminals. Moving now to the MCM or mini contact module. This device is used to monitor the contact status of an initiating device that contains a normally open contact, such as a pull station. The picture shows a pull station being monitored by the MCM. The MCM typically mounts in a single gang box behind the monitored pull station. When wiring the device, the front cover plate is removed to expose the wiring terminals. The SLC goes in and out on the same terminals as you can see in the drawing. The monitor device is wired to the other terminals as shown. A 5.1 k ohm resistor is provided and installed on the last monitored device. Remember to set the address for the MCM before connecting it to the SLC. The SCM-4 or single contact module is similar to the MCM in functionality. It is also used to monitor the contact status of a dry contact device. One of the differences between the MCM and the SCM is the size. The SCM mounts in a double gang or 4-square back box. When wiring the SCM-4, the SLC wires go in and out on the same terminals. The contact input is wired normally open to the terminals on the other side. A 5.1 k ohm resistor is provided with the device and should be installed on the last monitored device. Remember to set the address for the SCM-4 before connecting it to the SLC. DCM-4 or dual contact module is very similar to the MCM and the SCM. The SLC terminates the same. The end-of-line resistor is the same, 5.1 k ohms. The big difference is it can be used to monitor 2 contact points, each with a unique address. It uses 2 consecutive addresses. The unique addressing allows the points to be programmed individually if needed. The DCM comes from the factory to be wired Class B and monitor 2 contact points. It can be configured to monitor a single contact using a Class A wiring method. When configured to monitor a single contact, the DCM only uses one address. There is a jumper on the device next to the SLC terminals. Simply move the jumper over to set the device up for Class A wiring. Again, remember to set the address for the DCM4 before connecting it to the SLC. The default setting for the MCM, SCM, and DCM is Contact Input Pull Station. When configuring the device in the software, you determine what the device will be monitoring as a dry contact input. Anything from the list as seen here can be chosen in the programming software. Contact Input Pull Station, Water Flow, Supervisory, Tamper, Fire Drill, Trouble Monitor, Input Aux, Reset, Silence, Fire Alarm, Disable Inputs, Disable Outputs, Disable Inputs and Outputs, Lamp Test, CO Alarm, and CO Supervisory. For more information on configuring the MCM, SCM, DCM in the software, please refer to the recorded modules on the programming software. The TRM-4 or Twin Relay module has two Form C relay contacts that can be programmed to activate through the panel's programming software. This device is commonly used in elevator recall applications, damper control applications, and air handler shutdown applications, as well as many others. The contacts activate simultaneously. The contacts are rated 2 amps at 24 volts DC and a half an amp at 120 volts AC. As you can see in the diagram, the SLC wiring is the same as the other modules. Remember to set the address for the TRM4 before connecting it to the SLC. The CIZM4, or the Conventional Input Zone Module, is used to monitor conventional initiating devices such as smoke detectors. It's commonly used to monitor existing 2-wire conventional smoke detectors. The device is listed for several conventional detectors, and those can be found on the CIZM4 datasheet. The module supervises the initiating device wiring and the wiring from the power supply connected to the terminals 24 plus and 24 minus. Power supplied to the terminals 24 plus and 24 minus needs to be power limited. The IDC or initiating device circuit can be wired either Class A or Class B. The module comes defaulted to monitor an IDC wired Class B as shown in the top wiring diagram. Usually around 20 detectors can be connected to one CIZM, but it's best to check the data sheet and the devices you are using to make sure. At the end of the circuit of detectors, an end-of-line resistor is installed. If Class A wiring is required, the jumper, shown in the middle of this device drawing, needs to be moved to the Class A position. The end of the circuit now returns to the device and connects to terminals labeled A plus and A minus. When the CIZM detects an alarm, it is latched until the fire alarm control panel is reset. Again, remember to set the address for the CIZM4 before connecting it to the SLC. The MOM-4 or Monitored Output Module is a programmable output to control power, which then in turn operates notification appliances. This device is commonly used to activate a remote notification appliance circuit. With the SLC, you will also need to bring 24 volts DC to the module to power the notification circuit. The contacts on the MOM-4 are rated 2 amps at 24 volts DC. If synchronization is required for the notification circuit, the MOM-4 is listed with the SMD10-3A module for Potter AMSECO synchronization, as well as 2 modules for Wheelock synchronization. Remember to set the address for the MOM-4 before connecting it to the SLC. The SCI, or Short Circuit Isolator, is our last module. This device is very similar to the AIB, the addressable isolator base, that we covered earlier in the presentation. It's used to isolate shorts on the SLC to help maintain the system's functionality in the event of a short occurring on the SLC circuit. As previously mentioned, on addressable systems, when a short occurs on the SLC, it prevents communication on that circuit, effectively rendering the entire loop disabled. When an isolator is installed on the circuit, it will isolate the section of the circuit where a short occurred, allowing the remainder of the loop to continue to function as normal. When wiring an isolator module, there are 4 terminals for the SLC connection, 2 for the incoming SLC and 2 for the outgoing SLC. Also, as previously mentioned, due to the power consumption when a short occurs on the system and an isolator, either an AIB or an SCI, is active, there are limitations to the number of isolators that can be installed on an SLC. That concludes our list of modules. That also concludes our module on the SLC devices. For more information on programming and wiring of the SLC devices, please refer to the installation manual and the other recorded modules. The next module in this series is Module 6, SLC Device Addressing.